Uh, it's my pleasure to welcome everybody to our second Jerome Schultz and Jane Schultz endowed lecture series. It's a real honor to have Martin Keller here from the National Renewable Energy Laboratory, NREL. I think I got the acronym matched to the words correctly. I want to just open with a couple words about the college and the department. The college has been on a really high growth trajectory since I joined in 2018. Our dean for a number of years before me, Reza Abashian, is here, who really established the foundation that we've been using to grow. We've gone from 3,400 students to 5,000 students. The number of applicants in 2018 was at 12,000. For this fall, we have 20,000 applications. The preparation of the students coming in is continuing to go up as we raise the bar to try to keep to the number of students that we can accommodate. We're getting stronger and stronger students into the programs. So it's just been a wonderful time to be dean of the college and be associated with all of this and being able to help lead the vision for some of this. I do want to say a couple of things about Jerry Schultz. Jerry was the founding chair of our bioengineering department. I heard more about Jerry's background that I was unaware of at dinner last night and some of his accomplishments. Jerry is still active, and the reason he's not here with us today is that he's teaching a capstone design course and the projects are being presented, and we just couldn't quite get this lined up so that he could be here, but he promises to be here next year. He was described at dinner by my colleague Val as really the founder of the field of bioengineering, coming in with both degrees in biology and degrees in engineering at a time when that was a really unusual combination. And as we all know, bioengineering has just grown tremendously and just immensely important. Today, we're really honored to have Martin Keller with us. And what I'd like to do is invite Professor Val Vulev up to give introductions. Before doing that, let me just advance this. There's a land acknowledgement that I think is just very important. We'd like to respectfully acknowledge our responsibility to the original and current caretakers of this land, water, and air, the Cahuilla, Tongva, Luiseño, and Serrano peoples, and all their ancestors and descendants, past, present, and future. Today, the UCR campus is home to many indigenous peoples from all over the world, including UCR faculty, students, and staff, and we are grateful to have the opportunity to live and work on these homelands. So again, we appreciate Martin Keller being here, and Val, if you would come up, I ask you to do some introduction.
Good morning, everyone. It is my pleasure to have Dr. Martin Keller, being the second Schultz lecturer, Jane and Jerry Schultz lecturer. And he's a biochemist. By training, he got his degree from University of Regensburg, cum laude, from what I read. Actually in microbiology, the degree is in microbiology. And but reading his papers, he was actually not sitting, as he was focusing on anaerobic species. And his Nature paper, for instance, is more chemistry than biology, talking about how to make peptide bonds in the primordial earth conditions and relating it to origin of life. And that's back in 1994. And I highly recommend for you to read some of his key papers from graduate school. Then he came to San Diego in 1996 in Diversa Corporation, where he pursued corporate career, but he still did research and development with huge amount of research, and there are still some nice publications that came out of there. He contributed a lot to the field, showing not only how to explore diversity, but how to find the diversity in the with microorganisms around Earth. And he, from what I read, he set up the platform, the microbiology or the microbiology platform for this biotech company, which is now known for drug discovery. And then in 2006, he shifted and he went to Oak Ridge National Lab. He took numerous leadership positions working in biology, energy, combining them in bioenergy. And I think from 2007, it was for 3 years. He was the director of the DOE Bioenergy Science Center, which, as we know now, after this center developed a lot of advancement, had to focus on how to use biomass and things are completely useless and we burn them, how to use them to make useful sugars so that we can use them in making fuels. And he may talk more about it. And then in 2015, he moved to Colorado as the 9th director of National Renewable Energy Lab. And his presence was well noticed. Basically, he had unprecedented growth. He doubled the number. So he doubled the number of contracts with companies, with industrial partners. That required doubling the number of staff because somebody had to do the work, and led to about $1 billion of raising of funding, of research funding. He's still, you can follow, he still although you may look at him as administrator, he's intellectually active, he has patents and publications coming out, and he still contributes to the field quite a bit. I think in the National Lab, there are 3 initiatives. One that caught my attention was converting electrons to chemical bonds, because I'm selfish, that's what I'm interested in. And that's a very serious, basically a very serious field of science that is more science than engineering of how to store energy. Because as we know, the quantum energy of the photons matches the energy of chemical bonds. And he's a fellow of AAAS. He's been a member of many boards, advisory boards. One of the interesting facts was that in 2022, he was named in Denver the CEO of the Year. And then in 2024, we're still 2024, he was the Lab Director of the Year named by the Federal Consortium of Tech Transfer for National Labs. So we're all looking forward to your presentation. And without further ado, the floor is yours, Mark.
Thank you, everybody. Can you all hear me? Is this good? So first of all, again, thank you for the introduction, and special thanks also to the Schultz family for sponsoring this, and it's a great honor to be second. And again, for students in this room, I always say, when I'm just listening also for this introductory, I said, so I'm very honest there, and I said, never plan your career. So plan your impact. If somebody would have told me this from me growing up in Germany, going to this university, working on the origin of life, that I ended up to be the lab director at NREL, and probably nobody, I never would have even thought about this. So that's again where we come back to the end, because look, for me, you will see hopefully what I'm trying to do here today to give you a very high level overview. I was debating, well, should I take some of the cases and go deep, or I was thinking, let's go very broad. To tell you a little bit about what we do at NREL and also put this into perspective, why we're actually doing this. We always say at NREL that we have to save our planet. So we want to create a better future. And that's, again, what I try to highlight a little bit with you today, because especially talking to the students in this room, you are the generation who have to fix what the last 2 generations probably screwed up. So no pressure, but we have to get it done. So building a clean energy future for the world. So the idea really is here also what we say to the world. Says CO2 molecule doesn't stop on borders, so it is a global problem. We only have one planet, so we have to look at this holistically. So I want to start with a triple planetary crisis. You might have seen this, the United Nations published this a while ago to say that there's 3 big crises going on in parallel, and they're all interconnected. Pollution, climate change, and biodiversity loss. And a lot of the intertwining and the linkage between this is a lot of time the way we're using energy here on our planet. So I want to just give you a few points, pollution. When you look at this is not just what we're emitting into our air. When we had just a wonderful meeting earlier today talking about plastics. So when you see that aquatic ecosystem plastics, will triple from 2016 to 2040. So I've seen some reports predicting that by 2050 we have more plastics in the ocean than the weight of fish. So we have a big issue there. So pollution is a big area. Some numbers here. So 99% of the world population breathes air which is exceeding the quality limits. So this is again a global problem. 9 million people die premature because of pollution, and this is also interesting when you look at the statistics. This is also air pollution, but also, for example, pollution in our homes in many countries where we're still having, how we preparing food is very unhealthy in many areas. So this is a big problem. When you look at the CO2, we all know about this. So increasing in ocean acidity, we come back to this one also on the species, waste. So pollution is a big problem. Climate change. Well, I don't have to talk too much about climate change. We're all aware. We're trying to cut temperatures down, to increase to 1.5 degrees Celsius based on the Paris Accords. I'm personally very skeptical. I think we might not be able to do this. I think we just zoom through the 1.5. So, oops, I don't know what happened. I still see it here. Oh, okay, that's a projector. So we will see this, and again, I just experienced this live myself. I mean, I just was in Dubai last week when the big storm, you've probably seen this in the media, I got stuck there. So we're seeing this massive, you have here in California, when you see the changes in our environment. So this is a major problem we have to deal with. A couple of numbers. 1.2 billion people will be displaced by climate by 2050. So when we right now in the US worrying about our southern borders, can you imagine what happens when billions of people start to move because they have to move, because they just cannot live in their environment anymore? 700 million people will be displaced alone by drought by 2030. We have an increase in disaster. That's also when people questioning this, I always encourage them to look up some of the insurance companies. So Munich or Zurich Re, Munich, look at their numbers and then look at this, how much money they're paying out based on natural disasters. So just numbers, just money. And you can see how this is like this hockey stick. And so when people questioning about this, so why do we see this increase in these natural disasters? And it's clearly linked when you then overlap this with the prediction of climate change and increase in CO2 level. It's completely correlated. So insurances show you sea level rise, we all know about this, and when you look at this, what happens in the Arctic. So climate change is really a problem. Biodiversity loss. So some people might say, well, why do we worry about some rhinos if they disappear? But this problem, of course, is much bigger. So just give you this one data, you might have all seen this, was it last year? The heat wave in Arizona, Phoenix, where you suddenly saw that beehives were melting away. They all died because it was too hot for them. The hives melted. And you all know what this means. If you're losing our bee population, guess what will this do on impact on food? So it's all correlated and connected. So 150,000 numbers on the list of the red list on our species. 69% of decline in animal population since 1970. What we're losing, 10 million hectares of forest destroyed every year. And again, the average decline in natural ecosystems. Corals, so our family, we're all scuba divers. I've seen this myself. When you go right now, and you've probably all seen the latest report, that over 60% of our reefs are now really impacted. I've seen this when you go, let's say, Roatan, it was in November. You go diving, it looks like you're walking in Colorado. It's all snow-covered peaks. All the corals on top are completely bleached and white. So as you all know, we had this big heat spell the year before, or this last summer, and it just wiped out the corals. So we have a problem. So what are we doing? This is again what I would say, NREL at one slide. So this is how we are seeing ourselves. So a couple of things I want to point out here. So in the middle, you see the NREL team. We call ourselves NRELians. So this is where we are a very tight community, because everybody working at NREL is there because we want to make an impact. We want to do the energy transition. We want to move this as fast and as quickly as we can. That's our integrator. That's where everybody at NREL, from the people driving our shuttle buses to the researchers, this is our motivation. Besides, we love to be in Colorado, go skiing, but this is our motivation. That's why the NREL team, NRELians, that's what we see in the middle. And then we have three big initiatives. And again, they come back, and that's what I showed you on this triple planetary crisis, where we had this over the last 4 or 5 years, where we're sitting now 6 years, sitting down and say, what is our strategic plan? And we wanted to do this normally, historically. When you create these plans, you do this always on kind of how money is appropriated. That's how we, the National Lab, work. And we said, let's throw all this out. Let's develop this strategic plan with a 10, 15 years outlook, what we actually as a laboratory have to accomplish to attack the triple planetary crisis. Interesting thing there, I mean, this is more this was all developed under the Trump administration, which was interesting. And the final thing is that when people ask us how much have you changed our strategic plan from the Trump administration to the Biden administration, we've changed zero. We just talk about this a little bit different, but I think the idea is still we need to move this energy transition forward. So big three areas: integrated energy pathways, electrons to molecules, circular economy for energy materials. So what does this mean? So let me walk you through this. Integrated energy pathways. You all see that we now starting to have this technology with wind and solar and batteries, and we're starting now to deploy this technology at a much faster pace. The problem still is on the systems integration. How do you, when you go and drive your electric car into your garage and you plug it in and it's going bi-directional and you can power your house, you're selling electricity to your neighbor, how do you integrate all this together? How do you do transportation and the energy you need in our buildings? Or how do you do this on our industrial energy demands? How do you create the energy systems of the future integrated based on this clean energy technology which now is being rolled out? So we will talk about this more during this talk, but this is probably about 70–80% of what we do at NREL. And this goes all the way from creating new materials in photovoltaics like perovskites, all the way to the cybersecurity to keep the distributed energy system safe. Big effort. Electrons to molecules. We will need materials and hydrocarbons for the very, very long time. The question is, how do you get them? We probably cannot afford to pump them out of the ground anymore, so we have to make them in a different way. In addition there, what we're predicting there is that electricity is becoming the cheapest way of energy, so the cost will fall more and more based on decreasing in cost, especially out of the renewables. So can you take this electron and make a carbon-carbon bond out of this? Can you create molecules? This can be materials like perhaps the different ways of doing plastics, all the way to jet fuel and SAF, what we put into airplanes. And then circular economy for energy materials. So a lot of times, recycling is an afterthought. So plastic is a good example. So great material, beautiful, perfect, but we just don't know how to recycle. So same issue right now, what we will face very soon is with batteries. So if you all drive electric cars, we have all these years designed our batteries for the lightest weight with the highest energy density. And now we're realizing, how do we get these materials back? Because if we all drive electric cars, we don't have enough materials. So we cannot just put them onto the landfill. So that's why the circular economy, the idea is that you designing the reuse of the material at a much earlier stage. We feel that this is very important. That's a sustainability claim. You all know that we're on a pathway to use 2 times the resources our planet provides. Well, we only have one planet, so it doesn't work. Math doesn't work this way. This is why we need to think and be smarter at an earlier stage to bring the materials back into our economy. This describes NREL at a high level. That's what we do in these different areas. You all know the National Lab System, 17 years, Department of Energy National Laboratories, 3 big different areas. So you probably all have seen Oppenheimer. So that's the NNSA labs like Los Alamos, Sandia, and Lawrence Livermore. They're doing the stewardship of our nuclear arsenal and a lot of other things, but that's the main mission. Then we have the more fundamental science labs like Oak Ridge or Berkeley or SLAC. So they're doing a lot of fundamental science, user facilities. And then there's 3 applied laboratories. So NREL, we are doing the renewable energy, energy efficiency, energy transition. Idaho does the nuclear work on our nuclear energy side. And National Energy Technology Laboratory in Seattle, they're doing carbon management and fossil. So our job as the applied laboratory is to bring technology and try to mature and scale it as quickly as we can, that it's getting then deployed in our economies. This is how we're summarizing ourselves. That's also why you see why we're working with a lot of industry. We're also doing a lot of work with universities as yourself, because we want to bring the technology together and see how can we scale it and de-risk technology at a faster pace to make an impact in the economy. Why? As you know, what I told you earlier, at NREL, we want to create a better planet, so that's why we need to get technology deployed into the marketplace. A little bit about ourselves. So we are right now 3,862 folks at NREL. You're seeing a lot of staff, postdoc students. So we have a lot of them. What I want to focus here on this one is partnerships. And again, what I said, we know that changing our planet is a pretty big task. No lab alone, no university can do this. We need to partner up. Even one country cannot do this. That's also why international collaborations are still so critical in our opinion. But you can see this, that we creating a lot of partnerships, a lot of them with industry. And there we're doing work from very small startup companies, programs, to the big guys like Exxons and Shells and the Eatons and name it. So why? Because again, the idea is to take this technology and scale it as quickly as we can to make an impact in our economy. And that's also seen in our facilities. So yes, we have very fundamental science facilities, such as the Solar Energy Research Facility, which does a lot of very fundamental work in materials for batteries, or also for solar, like perovskites. But a lot of our facilities are designed to scale technology. On the electricity, on the grid side, and that's very similar to what we toured today, is the Energy Systems Integration Facility. So this is a facility really dedicated to about 2 megawatts and integrate the whole system. There's hydrogen going to all the labs, there's the electrical buses going there. So it's all connected, it's all linked to high-performance computing, that we can take and integrate and study all this different, from inverter technologies to other types of devices, to really help industry. They come in and scale this to the next level. Our newest facility, so the Energy Materials and Processing at Scale, what we call EMAPS, same concept. This will be a facility, 220 million. We will break ground later this year. It's really designed to scale energy materials at a faster pace. Some of you who are in the engineering roll-to-roll is a good example. Can you create this and make solar panels, how we do newspapers with solar inks like perovskites? How can you take this technology and scale it at a faster pace? We always say it took 30 years that solar became from a dream where people said, I don't know, yeah. So there's some of these people in Colorado, as the NREL got started, and the people said, well, I don't know what they're smoking, but they say that solar one day should be an important developer for electricity in our grid. And nobody believed this. I mean, and well, now we are there. It's one of the cheapest ways, but it took over 30 years. We do not have 30 years. We only have about 10 years to get technology to the next level. So scalability will be a huge issue, how we can do this in a faster way. This is what this facility will do. And then, of course, we have a very large facility, Advanced Research and Integrated Energy Systems, or ARES, which goes to 20 megawatts, where we're then integrating all this, where we have wind turbines and solar panels and storage and huge production hydrogen with large electrolyzers, 2 megawatts, to really link in the integration to take this hardware and this loop data and then emulate very large systems. Why is this important? A utility will not put new devices on the grid because the voice will the lights go out. So they need facilities like this to validate, get them comfortable, emulate very large system before they roll it out. That's again why there's a lot of industry in this facility, and we will talk about this more. This is a little bit our science drivers. So we go from renewable energy, sustainable transportation, building, energy systems integration. We have a big portfolio. Over the years, NREL really expanded. Yeah, we talked about this. It started as the Solar Energy Research Institute, and then over the years grew. Then biomass came in, and now it is a very broad portfolio, but all focusing on this energy transition in clean energy. So let's talk a little bit at high level where we are. And again, I don't want to dive too much into any of this detail, but I thought it might be interesting to give you perhaps a high level how we're seeing certain of these elements develop. Solar, first one. So again, huge progress made over the last years. As you all have seen, production costs came really down, mostly because China did a really good job to integrate the supply chain, but well, we all benefited from this, more or less perhaps. But there is now a lot of work still to be done on solar. If you deploy solar at a very large level, what we're talking, things like supply chain of materials is a huge problem. Even the kind of durability. So we are now 20 years, so the idea is, can you even expand this? Can you make sure that defects are not impacting the efficiency of cells? How do we do this grid-forming inverters? I mean, that's a big thing linked to the deployment of solar. New materials going into solar, such as perovskite. Some of you might have seen this. So the idea is that you're creating this solar inks, which could be revolutionized the way we're making solar panels. Much, much cheaper. You would have solar everywhere. So story is, yes, we made tremendous progress, but there's still a lot of work ahead of us. And on a global scale, solar is seen as the kind of energy, electricity system which will be significantly increased in the deployment, but also the way is how do you create supply chain, how do you make all this happening, and how to continue to get this technology into the market. So a lot of work at NREL. This is still our largest portfolio in all the different areas, and great progress, still a lot of work to do. You see on the right picture here, this is a new, really interesting development also is agrivoltaics. So the idea is really, can you combine what's happened in wind? There are a lot of farmers now have wind turbines on their farms, ranches. Can you do the same in combining solar? Because we have a couple of solar gardens, and there's a lot of really good benefits by combining solar and growth of vegetables and other areas. So big areas happening in this field. Wind. Wind is the same situation. So as you all know, what is the machines getting bigger and bigger and bigger. I don't know what happened. So it might be just falling asleep. So in wind, so we are limited on land of transportation to get the devices to the site. So this is the limitation right now why we're not building larger wind machines on land, because we just cannot transport the blades from the factory to the site. Because even right now, when you look at the size, even a railroad turns are too narrow to transport the big blades. Tunnels are too narrow, bridges are too low. So we limited by transportation. How can you overcome this? Can you make them, for example, on site? Can you completely change the way we manufacturing wind blades? You have seen larger machines going out onto the ocean because, the ocean doesn't have any curves. You can just barge it out. That's the reason that offshore wind is getting larger. We cannot do this on land. New materials. Oops. Sorry. Right now, it's we optimized our wind blades on the current materials. So, but the idea is, can you use new materials for wind in the future? So, for example, can you use thermoplastics which then will be able to repair wind blades in the field? Can you completely change this? Can you make it more sustainable? You all know when you drive over to your area, there's wind blades laying around because a lot of times we don't know what to do with them. So even to transport them away is too expensive. So this is a big area. The kind of stress, the larger the machine's getting, the more stress you're bringing into the wind blades, because when you see this huge size, the wind is different on this side versus on the other side of the tip, and this creates huge stress on the machines. Also, if you have wind parks, we're doing this wake steering now, because we realized that the machines are taking the wind in a different, because they're creating all this turbulence below the machines. So still a lot of work will go into wind to optimize wind in the next years. Water power. Water power, very interesting. So this is, again, I would say technology probably 20, 30 years behind wind, but we also need to look into this. The ocean is not a good and nice environment. It's complicated there based on all these different areas. So a lot of work at NREL also going in on water. And you argue, well, we are pretty far away from the ocean, but they're still, of course, coming from wind. A lot of the kind of work is now moving over into the water power and seeing how we can do to accelerate this type of technology in the years to come. Geothermal. Geothermal is really interesting. Geothermal is going through this new renaissance, what we call it. So a lot of times people said, geothermal is dead. We used what we can do, but now it's over. But now what happened? Two things happened now coming together. Number one is that we having a better understanding of the subsurface. We have better models. We understand this in a level through high-performance computing modeling this in a way which was not possible, let's say, even 5-10 years ago. And number two is technology like horizontal drilling and drilling technology from oil and gas now is morphing into the geothermal space. So geothermal, we're seeing this, it's a huge push now. So we think that geothermal will significantly grow based on these two elements and is a really interesting way to combine with some of the kind of concentrated solar as an example. So there is a lot of new developments moving forward in geothermal. Good thing is also that oil and gas, the companies are getting now interested in geothermal as well. And then we also talked about this, that geothermal also could have a side benefits that we could take some of the minerals out by combining the two as well. Transportation, as you all know, and you have seen what you're doing here, so there's a lot of movements here. So first of all, bioenergy. Bioenergy is a very interesting field. It shifted over so that we not long ago tried to do bioenergy to replace gasoline. Now I think the movement is really to use bioenergy, biofuels, to replace jet. So we're going towards SAF, sustainable aviation fuel. This will be very important. I think bioenergy will also not only give us fuel, but also I think, which is even a more important element down the road, is materials. Because nature is very good in building carbon-carbon bonds. So how can we use some of these materials nature provides and move this into our supply chains? Hydrogen. And by the way, this is a picture up there on the right, which shows our Flatiron site. So you're seeing the size here. When we talk about this, all on the lower right side is all hydrogen. So Toyota put all this equipment up there for us to validate. So hydrogen is an interesting field because not long ago, people said you can do everything with hydrogen except making money. So now this has changed. So why has this changed? Because hydrogen is now a platform molecule. So not long ago, hydrogen was just designed for transportation. Now it goes into a lot of different areas like green ammonia, materials, e-fuels, even for clean steel. So hydrogen as a platform really increased. Even now, looking into this to use it as a storage molecule. That's also what you have seen, a lot of investment from the Biden administration into hydrogen. Europe banks everything on hydrogen. I think I'm a little bit concerned, especially Germany, that I don't know if it all will be on hydrogen, but it will be interesting over the next 10 years how hydrogen as a field will develop. We're doing a lot of work in hydrogen, from new catalysts on electrolyzers all the way to having the world record in a heavy-duty truck fueling station at our site and everything between. So fully integrated on hydrogen and going again to the systems integration all the way up to 20 megawatts, what you see in the right picture there. A lot of work, and we are describing this, that we're working into make, store, move, and use. In all these different areas, it has to be integrated. It cannot be one single pillar alone. Transportation and mobility. So, well, yeah, we will electrify our commuter traffic, but again, we also had this wonderful discussion before we came here about what happens to our ships and maritime, what happens to heavy-duty traffic. We electrifying, but then also we're looking for alternative energy molecules. A lot of work in there, so nobody really knows what will be the energy molecule of the future we transport around or even use, because we will not be able to electrify everything. So, for example, we will not, at least I don't think, electrify kind of a big cargo ship. It will probably not work. So how do we do all this? And this is how do we working and decarbonizing airports. So there's even a big discussion. We have a couple of big projects with airports where they're suddenly looking now that the whole business model is changing. Just you probably all know this. The biggest, or do you know what the biggest income is for airports? It's parking. Because that's where airports make the most money. So suddenly you take parking away, and that's already, they have seen this already through Uber, where there was a lot of the big airports see a decrease in parking. How will this new transportation impact their business model? So just as one of the examples where transportation integrated is a big challenge. Buildings and industry. So now buildings are very interesting. So research in buildings over the years was like, it was going on and off. And suddenly now it's fully back in the center. Why? Building are the kind of integrator on the so-called grid edge. So this is where a lot of things is now happening. You have solar panels on your rooftop, you have your electric car, you buy directional, you power your home, you're selling electricity to your neighbor, you have smart appliances, control your demand. So buildings as an integrator has completely shifted and changed over the years. So where building research now is going to have much broader scope from just building materials to now a much more systems integration within our buildings, and from a building to a subdivision to a big city, how to integrate all this. Super exciting research now going on in this area of the building technology side. Advanced manufacturing. So while you've probably all seen this, where we're seeing the shift, and there in the manufacturing side, yeah, we will automate this, we build robotic systems, yes, but the supply chain of the new manufacturing technologies will be one of the big issues, how we're integrating all this together, and that's probably what you're also hearing in the news now through some of the IRA funds. A lot of manufacturers now coming back to the United States, and now the big next issue is supply chain. If you have all these battery manufacturers, how do you make sure that supply chains are integrated? Right now, a lot of the materials are still shipped to China, getting processed there and then coming back. So this will be a big area on the integration of manufacturing, how we also integrate supply chain to adapt to the new clean energy technologies. Now, the energy systems integration. So first of all, let me start there with the energy security. And a lot of times we underestimating the issue there. So give you this example in our home. When we got our solar panels and then the next day I show up there and I'm seeing all these boxes on my garage, I don't know what's in there. So now I love it because I have my phone, I can check my annual production rate of my solar panels. Wonderful. Who else can look at my solar panel? And who can use my app I'm using to go in there and turn off the grid? You probably have seen also reports right now that our grid systems, a lot of the utilities, there's discovered, and that's public, I can share this. You've seen this or heard this in briefings, that a lot of our utilities have so-called sleeper software on the systems, where people can do really, really bad things. So how do we make sure, if we have a more distributed system, how do we keep this system secure? You probably have seen the reports that you can hack through a kind of tire sensor onto your car and drive a car towards a tree. But you can do a lot of even worse things on the grid, even coming in through an inverter which is mounted onto your garage. This is a problem. That's why security and resilience are a very important element. Strategic analysis. I will show you also a couple of examples where we built a lot of these new systems where now computing and modeling allow us to do this very large analysis of very complicated systems, which is a great step forward. 5 years ago, 10 years ago, we were not able to do this. And now we're reaching a level on this analysis, which will give us a lot of insight what to do. Deployment and decision support linked to the analysis. Now where we're going through very strategically to see how can we bring whole regions together and move them forward on this energy transition to make this much more clean. And I will show you a couple of examples. And then there's conversion and storage research. So look, I thought I'd use a few slides to show you and go into a little bit more detail what this really means, because storage is absolutely critical moving down on a clean energy transition, especially if it's distributed and linked to renewables. So a lot of work happened there in this area. First of all, on the lower slide, you see that our grid architecture is fundamentally shifting. Not so long ago, very simple, we had a big, let's say, nuclear power plant, lines to the consumer, and you used it. Now it's so-called bidirectional. So you have, what I said, smart homes, so it goes bidirectional. You have solar panels, but you also might produce electricity, use electricity. The system is completely changed. But again, moving now this forward, there's two important things to really bring this for carbon-free power systems by 2025. Two things which are getting integrated. Number one is grid modernization. So we're making the grid more flexible, automated, and efficient. So each of this, what I showed you, let's say your panel on your home or your smart air conditioner is a controllable device where you can control the grid on based on power electronics. So suddenly the way we're controlling the grid will be completely different. So we will be bidirectional. And then now you're combining this with energy storage, where we then see the large-scale integration of wind and solar. You provide a lot of this grid services and increased storage. What does this show you? So grid modernization and storage could save the US over 150 billion by avoiding the construction of conventional power infrastructure. These two things combined Another thing, 600 million investment in smart grid in building technologies, we talked about this, can provide about 6 billion flexibility in funds to not build power plants. So this is why modernizing our grid, combining it with storage, this will be a big step towards decarbonization of our power systems. Give you here a couple of examples what we need. So we need storage from short duration when we talk about lithium battery, different sodium metal halide, name it, but also long term, beyond 10 hours, even perhaps two weeks. This is now what's happening. When you look at this, even in the US, what's in the queue, you're seeing a huge increase based on solar hybrid, offshore wind, storage as a hybrid. You're seeing the gray boxes. This is where a lot of things are already in the queue, being ready to deploy it in the US by integrating some of the storage technologies. And this is, again, there's a storage shot out from DOE. So, reduce storage cost by 90% in 10 plus hours in 1 decade. So again, they like to do this little, what DOE likes to do. But that's, again, why storage is so critical, and combining this with the optimization and the modernization of our grid system. Other countries are doing this. Australia is moving towards 100% renewable in instantaneous generation. Australia, in the distributed side, we say that they're about 10 years ahead of us. So they're moving heavily, aggressively towards down this. Korea is doing this. Of course, we are moving this down. European Union is doing this. A lot of money goes into this kind of grid modernization technologies. Now, my pledge back to the universities right now, over the years, power electronics folks, people in this grid, in the engineering was not very popular. So we are limited, we have a lot, we need to catch up on this area because we do not educate as many scientists and engineers in this area. So we always say this, one school in China produces more of this engineers in this area than all the colleges provided together in the United States. So we are falling behind in this because it was not sexy. And now a lot of this is coming back because now with AI moving into grid controls, this is now becoming a really exciting topic. So hopefully more people move into this space. Equity. This, of course, now is a very good point. How to get everybody aligned and part of the energy transition? We always say, if you just do the energy transition for Beverly Hills, it will not work. We need to give everybody a chance to be part of this transition. We are working in over 3,000 communities because the key to get everybody along is through this community work to convince them that there's a benefit for them to be part of this energy transition. This is why community work is so critical to us. So I'll give you an example. We have a facility in Alaska, and I'll give you just one thing where work with communities why this is so important. Alaska, historically, a lot of their homes were built by people coming in from the lower states and built homes, which were inadequate, big issue on fungal contaminations in their homes, not designed for this community. What led to this one, that in smaller villages, where a lot of times 3 generations live together, the elderly people couldn't live in their homes anymore. They had to leave. They're leaving and going to the larger cities, which again in Alaska are far away, so a lot of times only by boat or by plane. And it changes completely the dynamic of the villages. So we walked in there and had this project with them to sit down and say, okay, what do you actually really need? So we designed with the community a home to see what would the home reflect this style you're working. And then it came down, as you know, to build these homes in these very remote villages is very complicated. I would say, what are the 2 most complicated areas in your homes? There's 2 areas. Number 1, the kitchen. Number 2, the bathroom. This is where the electricity is. This is where all your kind of plumbing is. This is where the core, it's complicated in a home. So building a sleeping area is easy. So the project came around that we say, okay, what about if you design the kitchen and the bathroom in a facility, in a container, and you barge it to these villages, and then you build the home around it. And this is now suddenly where you can teach the local folks in these villages how to build a home around it. It was so successful, and this was done in a couple of villages. It now is spreading all over these villages in Alaska, because suddenly they can design their requirements and their home around the two important things, which are kitchen and bathroom. So just give you this example that if you wouldn't work with the communities, you would never understood what they desire, what they need. So now how to do this and bring this to many other communities at a very large scale. One thing was LA 100. Some of you might have seen this, that we have done this study with LA to see what it will take, different scenarios to go to 100% renewable. This was one of these landmark studies. Two things happened there. So number one was that we could, of course, get all the data, worked with LA very, very close in partnership. And high-performance computing enabled us actually to do this, where you run every rooftop if you can put solar on, where you modeled every charging station in future based on traffic flow, where we modeled every fire danger on the transmission stations and the transmission lines, where we cited all the where would you put solar, where would you put wind. Again, 3 years. Now led it to this amazing study, followed then by a project to then see how do you then implement this. So give you this very example. If you just say, well, you're getting a tax incentive to put solar panels on your roof, guess what happened in many areas? If you don't have a tax base, it doesn't help you because you're not getting the money back because you're not paying taxes anyway. Or your taxes are so low that you will never get the money back. So how do you build now policies to enable, especially some of the low-income areas, to also benefit this? And this is very different if you do this in South LA versus Beverly Hills. And this is, again, what we've done over the last 2 years with LA to see what can LA do to set some of these new rules and regulations in place to let everybody be part of this energy transition. Puerto Rico. So the secretary then asked us, well, can we do this in Puerto Rico? And we've done this. We finished this just a few months ago. We were done with the secretary, 2-year project to roll this out. A lot of work with the communities. We had over 100 community organizations being part of this. Puerto Rico, very different than LA, had this big discussion. It's an island, very mountain, so we have very small amount of flat area where you could build solar farms. Big discussion, well, do you take this piece of land to build a solar farm, take it away from production of vegetables, as an example? Huge discussion in the community. So what we came in, look, we're not telling Puerto Rico what to do. We just gave the information to these communities. They say, okay, if you do this, this is the outcome, this is the cost. If you go to this plan, this is the outcome, this is the cost. So we could provide the research foundation and the information and the data for the communities to make their decisions. Long story short, so they came to this very nice compromise. This is now heavily, the structure, the implementation plan, now is heavily based on 2 things, rooftop solar combined with storage. So if Puerto Rico now moves down and build this, this will be the largest distributed system ever built in the United States. So we are very excited, a good response, and this is again where sometimes we as researchers and scientists, or in this case NREL, Puerto Rico does not trust the local government, and they don't trust federal government. But when we came in, we don't have an agenda. Look, our goal is not to sell more solar panels or to do X and Y. We are unbiased. We just provided the data and the analytical tools for them to make the right decisions. But that's so important why you need to bring communities into this discussion. So now the point is, how do you scale this up? So LA started, and we do Puerto Rico, now we do many others. We do this for Lithuania, we'll talk about this. We do this now for many different areas. So, but DOE then announced the C2C, clean energy to communities, to see what we've learned, how do you scale this and how do you reach many more of these communities? Because again, what I showed you, the key for doing the energy transition goes through these communities. If we're not bringing them along, we will not be successful. Net zero world. So that's now what happened. This was announced in Scotland at a COP with the president and secretary and NREL, where we said, okay, let's do the same concepts and implement this to countries to help them in this energy transition. And when you look at these countries being part of this, I give you just this very interesting data. So we were we had a meeting with Bill Gates and the energy minister from Ukraine. And we walked him through all this, and he said, look, Martin, I see that a lot of times your data are based on resilience, clean energy, the transition. The problem is we need to optimize our grid, not because of climate change. We need to optimize our grid because somebody throws bombs onto our grid. So, but same problem. How do you create a resilience grid, not based on storms or kind of a drought, but based on military activity from a different country? So what I can share with you, you might have seen this, perhaps if you follow this, that Zelensky made this announcement, that they're going to a distributed system. A lot of this data, which I can share here, came out of the Net Zero World activity, with there's 10 labs now engaged in helping them. Because, it's very simple. Well, if you have one big plant, it's very easy just to destroy it. If you have them all over the place, much harder to do. Makes a lot of sense. So this shows you that the technology on building this resilient system also enable us to think in a very different way. And that's, again, why we're working in this program. Ukraine is one, so there's Egypt in there, there's Argentina in there, Singapore, for example, is having this underwater project where they want to try to build cables across some of the neighboring states to integrate the grid together. So it's a very broad way of helping countries and provide the data to them to help them to think through this process, is how they can march the energy transition forward. And we, as the US, why is this important for us? I think it is now also important that we are strong in this area, because we don't want to give all this to China. So I think we need to be a strong leader in this area, because this will help US companies. This will help to provide us. And I think, yes, we should be the thought leader in this transition to help other countries to move forward. Same here in India. We're doing a lot of work with India, where we're modeling their system. And now when you look at this, you've probably all seen this in the news. They built the largest solar farm ever built. This is a lot of where we supported them also on the data, how this could be handled and integrated. So long story short, I'm pretty optimistic. Yes, we are on a good path. So now the key is, how do we continue this, and how do we keep our eyes on this transition? And this is my last slide. So please join us. So especially for you, for the students, check out NREL. A lot of the students, what we're seeing is that you all might not even know what the national labs are. You don't know the programs. I know when you look at our websites, it's freakingly complicated. Oh, I understand this. So I encourage you, look not only at NREL, but look at the lab as a system and see there is a lot of really cool opportunities at our laboratories. Of course, best cool opportunities at NREL. But again, that's, of course, I'm biased here. But again, we have undergrad internships, we have graduate internships, we have postdoctoral programs. We're doing a lot of work in workforce development. There's a lot of work going on here. Why is this important? Because we need the best and the brightest from all over the place to move the energy transition forward. So encourage you, check us out. Look at our sites. If you cannot find anything or don't know how to maneuver this, send me an email. I can push you towards the right people. They always say the national labs are not for everybody. The beauty is on the national lab that you adopt. So our scientists, let's say in 10 years, they do something very different than coming in. Not everybody likes this. Some people like to stay with one area for the whole life. That's okay. That's probably not the national labs, to be honest with you, because we are adapting. Our staff constantly evolving and moves into different areas. So if you're interested in looking and exploring and your career is moving you into different areas, check out the lab system, because I think it could be an interesting place for you. So with this, I hope I did okay on time, but thank you for the opportunity to be here. I always love to, as you all know, I live 10 years in San Diego, so I always came through Riverside when we went up to Idlewild and other areas. So I really appreciate this, and thank you for the opportunity. So I hope you have some time for questions.
Okay, questions. First, do we have any questions from on the Zoom attendees? Not yet? Okay. Any questions from the audience?
Thank you for an excellent talk. I noticed that you didn't say anything about nuclear energy. You want to say something about that?
Yeah. Okay, look, we are not doing nuclear research. That's Idaho. But of course, we're looking a lot into this integration between nuclear and renewables. And I say this. I'm very skeptical about nuclear. And I tell you, there's a couple of very simple reasons. Number one, it's just pure cost. Look at the costs right now. Give you Colorado, Excel, the latest power purchasing agreement. Wind with 4-hour storage, $24 megawatt hour. Solar with storage, $32 megawatt hour. Nuclear, $148. It's freakingly expensive. So what should we do? Two things. My opinion is that the move to this small modular reactors, some of you might have SMRs, in my opinion is the wrong move. They're still too big. There's still a construction project. You still don't know what the costs will be. I don't understand why we're not going and say, okay, we're building microreactors, and it's treat it like a battery. We have technology that you could build, let's say, a 5 megawatt microreactor, 2 container, you dump it in a place, you don't touch it for 10 years, and you take it away like a battery. Why is this important? When you look into where the grid will go, we don't need down the road facilities which are gigawatts, even hundreds of megawatts. We need to fill in the gap, and frankly, what we will see, I don't think that many regions in the US and also global will go to 100% renewable. We don't need that. So we can go with renewables to about 80, 85%, and then the rest we have to fill in with different technologies. Then nuclear could be an important element if we understand the cost. How do you do this? You need to make these microreactors in a plant that you know as a utility, okay, I can order a 5 megawatt battery at the cost of this. I can order a 5 megawatt microreactor. Oh, the cost will be that. So as long as we cannot guarantee this, I think it will not happen. And then, frankly, the other interesting element is now national security. When we were sitting with Ukrainians, as you know, Ukraine is very heavily in nuclear. They had some plans to build a small modular reactor. So I asked the minister, so look, I'm trying to get the cost of what the megawatt hour is for SMR, and I cannot get it. And so I asked the minister, so look, you want to build this? He said, what is the cost? And he looked at me, Martin, if you can get the cost, you would please let me know because we cannot get it. Because nobody will guarantee you the cost because, well, it's the first one, well, and that's fine, but still, because it's a construction project, it's very hard to estimate. And you all know, look at our reactors we just finished, the cost overruns are astronomical because it's so hard to, and where the energy market goes, look, when you order a 5 megawatt solar plant, you know exactly what the cost will be. Nuclear, nobody can tell you. Big disadvantage.
Other questions? George?
Just a really quick question to build off the microreactors and then the discussion you had about distributed energy. You focused a lot on Ukraine, and obviously there's some compelling reasons why you don't want centralized energy. But can you expand a little bit how that would fit into the United States picture in terms of disasters, wildfires, being able to build out the distribution in the U.S. itself?
Yeah. So look, I give you the best data right now on a pretty big area. I mean, we've done all this wildfire modeling for LA, and there I tell you it's very clear that every model, which is it makes sense. If you have a more distributed system, you increase the resilience of the system. So, for example, in Puerto Rico, after the first hurricane, the Trump administration came in and they had this plan to build kind of one central plant on natural gas, and then they would have done the same way to pipe the electricity over the mountain and distribute it. And guess what all the models showed? And guess what then happened with the second hurricane hitting? It just knocked it out again. It's logic. I mean, you have one line going over a mountain. If the line goes down, guess what? The other half of the island is dark. So now when you model this on a distributed system, and especially when you go down on the combination of rooftop and storage, especially, and this again where the plan is, where you're building this out in the remote areas at the end of the lines, because this is which in the situation are the most vulnerable people to getting blackouts. So this is the way to go, because by definition, you increase the resilience. I tell you another model just close to you all. We have done this for Bakersfield. Same situation there. A lot of these rural communities are at the end of the lines. Guess what happens if there's a blackout? They're cut. Problem then is that a lot of these people to go within, as you know this better than I do. I mean, it's not necessarily cool here in the summer. So if you have a blackout in the middle of August, guess what? After 2 days, all your food is gone. And then, so for low-income families, two whammies. I mean, they have no electricity, their food is gone. It takes them forever to go to a grocery store. And by the way, they don't have the means to replenish all this. So this is, again, why if I would have a magic wand, I would love to take politics out of this, because a lot of this makes so much sense. Combining this, where now we get into this point where, from a cost structure, it's no-brainer anymore. That's, again, why I tell you what I would support. If people say, well, we want to save the planet by solar. Wrong line. Well, yeah, of course we want to save the planet. But it's an economic benefit, especially for rural America. It makes sense to have a solar, have some storage, combine this, distribute out in the rural America, and make it not dependent on a line going in. Another example to finish this is Borrego Springs. Borrego Springs, we've done this large project with them where we got the data live to NREL, where we modeled and showed them on live data. As you all know, Borrego Springs, one line in, they constantly had this problem that if something happened, this one line got knocked out and Borrego Springs had no electricity left. So they built this, they built a distributed system, they put storage. We showed and modeled with them how much storage they need. The amount of blackouts significantly decreased. So the way to go to a distributed system is the future. So now let me show you the other side, because especially, again, not talking about politics, but we're hearing this, that a lot of people in California argue, well, we don't need a distribution system anymore. It can be all done distributed. No, it cannot. So we need to have a kind of transmission lines. We need to have a transmission system. Why? Because now when you look at this holistically, so we have areas where there's not so much sun or wind. So we have to have lines to distribute our system. That's why you need to have a distributed energy system in combination with the increased lines of shuttling electrons around. Texas would not have had this problem when they all had this cold spell if they would have been connected, because it just was Texas. I mean, Colorado, we didn't have the issue. We had enough electricity, but there's no way to bring it to them because they're almost like this island. So build transmission systems and integrate this with a distributed system. But to manage and regulate this will be very different. And that's, again, why we need this work.
Other questions?
All the above. So look, unfortunately, I cannot go into a lot of details here. But I tell you, the very simple system is that the new kind of power electronics systems. Look, I mean, as you know, how we're controlling our grid right now is very simple. We have big masses spinning, and especially when you do a black start. So the grid goes down, you have to bring it back up. The way it's done right now is that you have this big masses rotating. I mean, this is a generator, a big masses rotating. This is then where the frequency, you control this and you get the grid back up. So if it's all done on solar and wind, for example, you cannot do it this way. So this where you have this big research in what's called grid forming inverters, so that you have inverter technology which will help you to rebuild your grid if it goes down. So having a lot of these devices on our system is amazing because we can control it in a level which is different. Give you an example. Eastern grid, Western grid, Texas. Western grid is controlled right now with about 10,000 controllable points. That's how we control our grid. So we modeled this for the Bay Area with new power electronics coming. So for example, every charging station is a controllable device. Every smart heat pump in your house will be a controllable device. So the Bay Area alone has right now about 2 million controllable devices, which we can help to control our grid. Very different system. The problem is that each of this controllable device can be used to kill your grid because it's a way to get into your grid. So the problem is twofold. You can use these devices to control the grid in a much better way, but humans cannot do this anymore. Because if you right now are sitting in a control center and turning knobs and you have 2 million in one area, no humans can do this. Will lead to automation in this area, which will lead to artificial intelligence, machine learning algorithms to control the grid of the future, which brings new danger. Because if you have this done by a software, guess what? If somebody, so you can say, well, no, we don't want this. Let's stay with all coal plants, which are all analog. This also doesn't work because all of you, when you look, you take your phone to open your car, you're checking your energy demand on your house. We all moving down, the customers demand more control of the system. I don't know how many of you have hue lights in your homes. Well, I love it because then I can, while I'm gone, I turn them on, I turn them off, I change color. I love them. It's much safer to have a switch, yeah, but we moving down this path. This is why we cannot say, well, we don't do the transition. We as humans, look at all of us have smartphones. None of you probably has flip phone left. Flip phone is much safer based on cyber, but well, we move to the smartphone. So this means saying, no, we don't do this is not a solution. We just have to be ahead and do it smartly. And this is why security is, I tell my kids, if you want to have a job but you will be never unemployed, go to cybersecurity. You will always have a job because this is constantly, you will never finish this because it will never finish. So, and the demand through AI will just skyrocket. Yeah, it's on now. It's on now. Yeah. 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 I think it's working. Yeah.
Hello, can
Yeah.
you? Yeah. So I'm Amna. Good morning, everyone, and thank you. It's a great talk. So from the perspective of the community, right? If all this great work it goes out and a community is implemented, how do you see it? Like, what's the impact on the community members, or how does the life changes? Like, do you see any changes, any impacts to the community if this great work goes out, and how does it improve them? How does it improve their lives?
Yeah. Look, you completely nailed it, how we can make the energy transition a success. It has to improve the quality of life for the people. And so what are the elements? So number one is cost. Because look, what we sometimes forgetting, that when you go, look, when people sometimes, well, nobody worries about this, they just never, well, if you're living and if you have a hard time to know how you feed your family tomorrow, you're not worried about climate change in 30 years because you worry about tomorrow. So the same if you say, well, now we have it all clean, but now my cost to cool my house goes up 3 times. People say, I don't want this because I cannot afford it. So affordability is one of the biggest driver. I think there's still this where we have to work with the community to show them that we also have to watch out for our environment. Look, I think I would argue that this awareness is increasing. We in the US are behind. When you go to Europe, it's not even a topic. Here we are behind, but people, I would say, broadly speaking, so they just define this in a different way. And I give you this example. When I lived in Tennessee, we had a little farm, and our neighbors constantly complained about, I have to put larger gravel on my driveway because every year the rain is washing it out, and I need to put bigger one on because the rain is getting stronger. Yeah, but this is, that's the way they describe climate change. So if I would go there, say, well, you're talking about climate change, I would lose them in 1 second because it's politicized. So how we as scientists, how do we pick up the communities where they are and bring them along this journey? Look, and this is again where I think it's so critical. To give you this, again, coming back to communities like we're doing work in Bakersfield. As you all know, very conservative, oil and gas driven. So sometimes we scientists do not understand how we talk to these communities. That's again why what we're trying to do there is we have about 80 people kind of in community work. First of all, you need to send people to the community who understand the community, speak and look like the community, because you need to build trust in the community. A lot of times we cannot do this. That's why you partner with community organizations to bring them on this journey. The other part is that this is taking time, and you need to pick up the community. Sometimes, and again, so you're seeing this, well, everybody needs to go to 100%, whatever, and that's not the path. So if your community just wants to put an electric charging station and they don't know how to do this, that's okay. Help them on this journey, pick them up where they are and move them along. I tell you now what keeps me up at night. About 45,000 communities in the United States. Each of them, it's a contact sport. We know how to scale algorithms. We know how to scale computing power. We know how to do that to make our models faster. And work with communities is not scalable in the way we're scaling computing code, because it's a contact sport. It takes time. It takes trust. It takes individual work with these communities. And how do we do this? This is what really worries me, because we cannot just automate this. We cannot scale it. We need to do this, that we teaching the communities, hopefully then bring people who then go to the next community and build a system, because this is what I call contact sport. So now you're combining the great models we have, analysis, where we can answer a lot of these questions, but we need to give them the assistance and the support and the kind of foundation to move them forward. And this is not scalable. That scares me.
Thank you.
We do have a Zoom question.
Yeah.
Do you have any insights on agrovoltaics, and would also like to learn more about perovskite work at NREL and agrovoltaics with PV, wind, geothermal, etc. I'm only a little bit familiar with USDA and DOE collaborations in the area. And thank you for the lecture.
Yeah. So agrivoltaics, look, this is a very interesting field. So as you know, what happened, sometimes we're forgetting this. Wind saved a lot of family ranches and farms. So because, look, when you go to Kansas, you're seeing this. I mean, look, perfect. You're a landowner. You're saying, hey, I give you the right to build a wind park here. I still drive a tractor around the wind farms or the wind machines, and you're getting revenue by having this on your site. Great activity. Look, right now sometimes it's shifting, but in general, farming communities are very supportive for wind because it brings them extra revenue. So now solar is a little bit different, because if you're a solar farm, you cannot drive a tractor through there anymore. So this is now where the work comes in. I tell you, we have a very large solar farm in Colorado, and I was there, and I give you this one example, especially when you grow vegetables. So sometimes we're forgetting this, that our plants, in the summer, we have too much sun to our plants. So salad, good example. You cannot grow salad outside of Denver when you go towards Kansas, because it's too hot and it doesn't grow anymore, because it just shoots, boom, and it's bitter, it doesn't work. So on agrivoltaics, I've seen it, tasted it myself. You can grow salad the whole year round, because the shade is cooling the area, is decreasing the amount of sun radiation the plant gets, and you can grow it all year till winter comes, of course, but it tastes perfect, it doesn't taste bitter, and you do the comparison. So there is now more and more data coming out that the combination is beneficial also to the solar, because the plants underneath is cooling the solar panels. If they're cooler, I mean, again, if they're getting hot, the efficiency goes down. Big effort in irrigation, because you need much less water when you have irrigation, because, I mean, it's just not so hot. So then the question is, how do you space the panels? Are you elevating them, that you can, let's say, drive specialty tractors underneath it? So this is where a lot of this research goes in. And then again, this is where we're getting a lot of interest right now from even, let's say, the MENA region, where they're looking into this to combine the two elements. So I think agrivoltaics still at the early stage, but this can be an interesting way specifically for family farms. When you go to smaller areas where we grow vegetables, which is still a lot of manual labor, a lot of the vegetable farms don't even use tractors. So combining these two, finding the right kind of height, distance, what crop do you grow? This is the research we're doing right now with some of the farming communities, and we have the solar farms and partnerships in many different areas. So Arizona is very different than Denver, is very different than let's say, New Mexico, kind of New Hampshire. So you need to understand this, but it's an interesting field. So perovskites. So perovskites is evolving very, very quickly. I mean, it's again this what call this organic materials which you can use as an ink. So you can put this onto a system, and then it forms this stage to then be a solar panel. Problem there twofold. First of all, was efficiency. So a lot of work is done in this area to increase efficiency. Works really good now. And then the second issue was stability, because these molecules are very sensitive to humidity. So how do you make them more stable? How to encapsulate them? So now the first solar kind of perovskite kind of panels are making slowly entrance into the market. It will be a tandem where you use current technology and you put a perovskite film on top of this, increasing efficiency. So this is where we're working with a consortium with some startup companies and some established companies to accelerate this. But it can be a game changer in this area. Very, very exciting research. Again, problem there is it's a race. China spends about 10 times the amount of money in this area than we do, we as the US. So this is a race who comes with this new formula and this new manufacturing way. Thereby, roll-to-roll is so important because you would make it like literally like newspaper. So this is where the race is on, how to scale this technology and how to bring this to market fastest. Problem then is next level is bankability. As you all know, if you say, hey, I need a loan, I said, yeah, okay, how long is your technology last? Well, I don't know. You will never get money. So this is the big issue about bankability, where you do this matured aging, where you show, yes, this will work for the next 10, 20 years. So this is now the next big race in this technology to move this forward towards bankability, which we have this problem in the US. China doesn't have this because they just do it. But for us, bankability for this technology is a big issue.
Other questions? So, oh, it's not you.
No, it's me.
Okay. Actually, I reserve my questions and you may expect, but one of the things is you already mentioned one of the initiative to photon to chemical bond. And what is your opinion? And I mean, that's been debated. So last night we discussed e-fuels versus solar fuels. What's the advantage of having e-fuel type of system when you have light harvesting, well-established technology, electrolysis of water, well-established, synthesis well-established, they're all separated modules, or we have the other that many Europeans and also American groups, I mean, Jerome and others, they push it to have everything in one box, where you shine light and you get the fuel, the liquid fuel out without any modules.
So if you have the technology to create a 1 million gallon plant in 2 years, let me know, and I invest in your company. So because the problem is, look, the problem is we have the fundamental science, but the cost is not there, scalability is not there. So will this come? Absolutely. I think that's where we need to push the research. Right now on e-fuels, where we are is in bolting together certain technologies to go to this. I think this will be easy, I mean, closer to full commercialization. It's sometimes hard to get these numbers. I mean, I would say in Europe, they are further ahead than we are in the United States. But right now, you look with current technologies, bolt them together. People say that we roughly at about $9 to $10 a gallon. So where do we need to be? 2 to 3. So, but let's look from a science. That's not astronomically. Yeah. So we can get there. So what is still the problem? So first of all, the systems integration, we still don't understand. If you, let's say, do solar panel and you do electrolyzers, the way we're changing AC, DC, AC, back and forth, and it's not, we need to do the systems integration. There's still money we can take out. The big issue is then on the catalyst. A lot of the processes are creating a mixture of different hydrocarbons. And then a lot of the cost is coming in the separation of the individual molecules at the end. So if we would have more specialized and targeted catalysts and drive the reaction to not this wild mixture, but more defined mixture, it will significantly decrease the cost. So what our discussion was, we need better catalysts, we need better systems integration. But I think this field will come. And then, of course, on the carbon capture side, you all know this. I mean, there's a lot of research we still have to do. The catalysts are, the lifetime is not there. They're using too much energy. So there is also still some fundamental science we need to do. But we need, this will come. I think this will be where, in our view, biofuels will morph into e-fuels. And this is the only way we can scale it to replace transportation fuel, and especially airlines, SAF. So biomass alone, globally spoken, will not be enough. So it will be a good transition, and then we need to do something which we can scale at larger scale, and that's, in my view, e-fuels in certain areas like MENA region, Patagonia, Atacama Desert, perhaps here in Arizona. So this is where I think the trend will go on organic hydrocarbons.
Other questions? Yeah.
Just wonderful presentation and great discussion. For all of the researchers here and some of the future researchers here, can you just say a little bit about how they might go about working with NREL on proposals or collaborations?
Yeah, so look, it's hard to work with the national lab system. I get it. It's complicated. And look, I mean, NREL, we're trying to make it as simple as we can. I think we made a lot of progress, but even there, it's complicated. A lot of times, to be honest, on the tech transfer offices are sometimes not helpful because, look, I always say this, even to our own people. This is my pet peeve, where people worry about IP and all this. And it's okay, tell me one technology in the energy sector who made billions of dollars by tech transfer. Historically, across our country, most tech transfer offices are actually losing money. There's a couple of good examples out there. Gatorade is one, but you all know this. Gatorade was not a patent, it's a trademark. So what university did there? In the pharmaceutical industry, yes, if you have a drug, there is, but in the energy sector, a lot of times the time and the cost and the patents is not where you make a lot of money. So I always say, what I tell our people, let's hopefully overcome these IP issues and let's really worry about this, how we accelerate the energy. So this is, I know it's a little bit delicate discussion there, but a lot of times on our side and also on the partnership with the universities, we're seeing this as an increasing hurdle because you're doing an agreement and the first thing you're walking into their office is, okay, I need action. Why? Because what we do there will create billions of dollars. And I say, yeah, okay, perhaps. I hope. I wish you the best. So the key is, how do we do this faster? On our side, on the university side. And then the key is, for example, on the research partnerships. As you all know, if you see some applications, call us up and talk directly. I think for me, the best way always is on the research-to-researcher interactions. And this comes back to, look, we all know this. You're not getting jobs, let's say, by looking in nature science. So you're getting jobs because you know somebody who then helps you. That's the same on the research proposals. The best one is if you know somebody at NREL, you call them up and say, hey, I have this idea, should we collaborate? We have done this with the university to put these umbrellas in place and all that, yeah. But I think the real, in my opinion, where you really see progress is if you all working in a place, find people at NREL and connect, call them up. And we do this a lot of times, and I know some of the proposals we have together are created this way. So I just would encourage you, when you go and look at some of the opportunities, especially, I mean, that you all know this, it's not a secret, I think. If you have DOE opportunities, especially in the applied programs, there's a lot of times a benefit if you collaborate with a national lab. Yeah, and we love it, and I think it's a win-win. So encourage you, make the connections, seek us out, and again, if you try to do this and you're not getting an answer from our scientists, also let me know, because sometimes, same on your side, we're all so busy, but in my opinion, the direct connection between faculty and our staff, this is where you accelerate partnerships. Yeah.
Yeah, so just a add-on to that. You had a big piece of your pie that you were funded from the federal agencies. So is it primarily the Department of Energy, or is Department of Defense and EPA and the National Health? I don't know who primarily in the federal
So-
world funds you.
So this year, our budget is about 960 million, roughly, plus minus. Out of this 960 million, about 140 million is coming from industry and other agencies like DoD, and the rest is pretty much across Department of Energy. There, most of the ERE, energy efficiency, renewable energy, but then also we get money from Office of Science, BRBS, Oscar, but this is all DOE funding. So DOE is roughly 85%.
Okay, so let's thank Martin again for the wonderful talk.